SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering, and today we shall discuss about the mass flow rate. In fact, in the last class we have started deriving the expression of mass flow rate of steam through a nozzle, and then we will discuss about the critical pressure ratio. So, if I can recall, in the last class we started our discussion on the mass flow rate of steam through a nozzle. So, this is the nozzle and there is a flow of steam through the nozzle. And this 1 refers to inlet and section 2 refers to outlet. Okay. So, now I mean in the last class, if we can in fact again write the expression. So, by applying the steady flow energy equation, we could write C dC plus dH equal to 0, right. So, this is equation number 1, that is what we had written in the last class as well, and this equation is obtained from the steady flow energy equation applied between these two sections, that is section 1 and section 2. And we have assumed that the length of the nozzle is short, so that the change in elevation between these two sections can be neglected. And also we could write the property relation, which is TdS is equal to dH minus VdP. This is for any process at any state point we can write, since the process is isentropic. So, the flow of steam through the nozzle is modeled. So, this flow is modeled by an isentropic process, and that is represented mathematically by this equation that you have studied many times, equal to P by rho to the power k, where k is index of expansion for the isentropic process that we have considered. Now, if the process is isentropic, we can write dH equal to VdP, that is dP by rho, and so this is equation number 2. So, if we write the expression of dH in equation 1, then we can write from this equation C dC equal to minus dP by rho. If we integrate between these two sections 1 and 2, that means when the stream is flowing from section 1 1 to section 2 2, then the change in velocity, that is 1 to 2 C 1 to C 2, and what would be the change in pressure. Since again let me tell you, it is not a flow of an incompressible fluid, rather the flow is of a compressible fluid. So, this pressure and density, these two are related, and that is what we have written over here. It is modeled like this in this using this equation. So, if we go to the next slide, we can write that integral 1 to 2 CdC equal to 1 to 2 dP by rho. So, we can write C2 square by minus C1 square by 2 equal to C 1 by rho, that is I can write P by rho power k equal to constant. Therefore, 1 by rho equal to constant power 1 upon k into 1 upon P 1 upon k. So, this is the expression that we can write. Okay. So, if we write it, we can write minus constant power 1 upon k into 1 to 2 dP by P upon 1 upon k, dP by P power 1 upon k. So, this is the expression. Now, what we can write? We can write this equal to constant power 1 upon k 2 to 1 dP by P upon P power 1 upon k. So, if we go one step further, just we can write that is constant power, constant to the power 1 upon k into, it would be P 1 k minus 1 upon k minus P 2 to the power k minus 1 upon k divided by k minus 1 upon k. So, this is very straightforward and trivial as well, and minus 1 upon k. So, this is the expression we can write, right. Now, what we can write, just we can manipulate, you know that we can write this constant to the power 1 upon k equal to, so let me write here. So, this quantity is P to the P power rho to the power k equal to P 1 upon rho 1 to the power k, that we can write. This is also I can write like this, equal to constant, right. So, if we go one step further, we can write C 2 square minus C 1 square upon 2. This constant is P 1 by rho 1 to the power k power 1 upon k into, we can write P 1 to the power k minus 1 upon k minus P to the power P 2 to the power k minus 1 upon k into k by k minus 1. So, this is the expression. If we go one step further, you know, we can write this is the expression should be. So, basically we can write C 2 square minus C 1 square by 2 equal to k upon k minus 1 k upon k minus 1 into what we can write. So, this is P 1 power 1 upon k and this would be 1 by rho, that rho 1. So, we can write it, that is P 1 into 1 by rho 1 P1 power 1 upon k, and this it is rho 1, just rho 1, right. This is just rho 1, we can write rho 1, and we can take P1 power k minus 1 by k from this bracket. So, we can take this particular term out from this bracket, then we can write P1 power k minus 1 upon k. Our objective is to write, so this should be 1, so this should be 1 minus P2 by P1 power k minus 1 upon k. So, this is the final expression. Now, we can write k upon k minus 1 into, it should be P1 by rho 1, this is P1 by rho 1, and 1 minus P2 by P1 to the power k minus 1 upon k within bracket. So, this is the final expression of change in velocity of steam as it passes through a convergent nozzle. So, you know that if we go to the previous slide, the cross sectional area 2 is much less than the cross sectional area 1. So, if we calculate the velocity of steam at both sections, we will find that the velocity of steam at section 1 is much less than the velocity of steam which is there at section 2. So, you know, we can, what we can do from this order of magnitude analysis, we can write C2 is much less than C1, right. Sorry, C1 is much less than C2. Velocity at section 1 is very is order lesser than the velocity of steam at section 2. If that is the case, we can write this expression that C2 square by 2 equal to k by k minus 1 k by k minus 1 into P1 by rho 1 into 1 minus P2 by P1 to the power k minus 1 upon k. So, this is the expression. So, you know, if we go one step further, we can write what would be the velocity of C2. So, C2 square equal to 2k by k minus 1 into P1 by rho 1 into 1 minus P2 by P1 to the power k minus 1 upon k. So, this is the nozzle, this is the section 1 and this is section 2. Right. What are the properties at section 1? Properties are C1, rho 1, H1, T1, P1. Similarly, properties at section 2 are C2, rho 2, H2, T2 and P2. So, these are the properties at section 1, right. So, what we can see, you know, that we are interested in the velocity of steam at section 2 that is C2, and that is what we can write C2 equal to under root 2k by k minus 1 P1 by rho 1 into 1 minus P2 by P1 power k minus 1 upon k. So, this is the velocity of steam at the exit of the nozzle, right. So, this is the velocity of steam at the exit of the nozzle. C2. Question is, once we have calculated the velocity of steam at the exit of the nozzle, we also can calculate the mass flow rate, because we wanted to have the expression of mass flow rate of steam at the exit of the nozzle. That is very important. Now, what we can see from the expression that we have established today, that velocity of steam at the exit of the nozzle, k is constant. So, you can understand k P1 rho 1 and P2 by P1. So, this is the pressure ratio. So, this P2 by P1, that is the pressure ratio. So, that is the ratio of exit pressure to the inlet pressure, and we also can see the k, that is index of expansion coefficient, and P1 by rho 1. So, what we can write, that from this we can understand that P1 rho 1 k, these are constant, right. Why? Because that we can write from this particular expression, if this is the nozzle, we know what is the steam pressure at the inlet to the nozzle, because that is the pressure of steam at the exit of the boiler. If we can fix the temperature pressure, then density will be constant at that particular location. So, if the pressure, density and this constant, this index of expansion, these three are constant at the exit of the inlet of the nozzle, then we can see the exit velocity is function of P2 by P1, that is pressure ratio. So, under this condition C2 is only the function of pressure ratio P2 by P1, right. So, why not to look at the value of P2 by P1 for which the velocity of steam at the exit of the nozzle should be maximum. Try to understand, if we try to recall exactly what we have discussed, in one of the previous classes, that the velocity of steam at the exit of the nozzle is very important. In fact, the steam turbine is the assemblage of flow nozzle and turbine blades. When steam is entering into the flow nozzle, our main objective is to increase the kinetic energy of steam, and that kinetic energy will essentially depend on the velocity of steam at the exit of the nozzle. From the expression that we have derived today, we can see that the velocity of steam at the exit of the nozzle will is dependent on so many parameters like pressure, density at the inlet, index of expansion, along with one particular ratio, that is the pressure ratio. Since P1, rho 1 and k, these three are constant at the inlet to the turbine, at the inlet to the nozzle, because we are maintaining that pressure will be constant, that is the pressure of steam at the exit of the boiler. If we can maintain the temperature and pressure, these two are constant, then probably density will remain constant. So, only you can understand the velocity should be, velocity is the function of pressure ratio. So, then why not to look at a particular pressure ratio for which the velocity will be maximum, and that is what that should be the objective when someone is designing the nozzle. So, knowing the pressure of steam at the inlet of the nozzle, someone should try to calculate what should be the pressure ratio, that means what would be the pressure range of operation for which the flow velocity at the exit of the steam should be maximum, which in turn will have the maximum kinetic energy of steam jet which will come out from the nozzle. If we increase the kinetic energy of jet, and if we can deflect that particular moment, that jet in when that jet is striking the turbine blade, we can have higher momentum, and that momentum change, and that momentum will be absorbed by the wheel of the by the rotor of the turbine wheel, and from there we can get work output. So, objective should be now to look at the magnitude of this particular pressure ratio for which the velocity of the steam at the exit of the nozzle will be maximum. So, now let us consider that P2 by P1 say equal to R. So, this is the pressure ratio. So, this is P and this is P1. So, this is the pressure ratio, and our objective should be to find out the value of R, rather the critical value of R for which the velocity would be maximum. If you would like to do so, then again if we go to the previous slide. So, this is the expression of C2, then what would be the mass flow rate? So, mass flow rate through the nozzle, mass flow rate per unit area. Let us first write the mass flow rate through the nozzle. Mass flow rate through the nozzle m dot 2 equal to m dot 1 equal to m dot. So, this is what we can write from the continuity equation. Okay. So, this m dot 2 is nothing but rho 2 A2 into C2, right. So, if we can have this is the expression of rho 2 A2 into C2, then we can write. So, that is A2 and then rho 2, let us P1 by rho 1 power k equal to P2 by rho 2 power k equal to constant, right. So, we can write rho 2 equal to rho 1 into P2 by P1 power 1 upon k into C2. So, basically we are writing rho 2 equal to rho 2, that we are getting from this expression, okay. And that should be multiplied by C2, the expression of C2 that already we have derived in the last slide. So, C2 is this. So, if we write the expression of C2, what we will be getting? We can write that into 2k by k minus 1 into P1 by rho 1 into 1 minus P2 by P1 to the power k minus 1 upon k power half, right. So, what we can do now? We can try to simplify this expression, then we will be getting that will be equal to A2. We can take this particular this factor inside the root, then what we can write? We can write, so this should be rho 1 square and rho 1 power 2 by k. So, we can write it P 1 into rho 1. If we give the total under root, okay. So, this is P 1 by rho 1, we can write it equal to A 2, then we can keep. So, this rho 1 should go inside, then it should be rho 2 square, and this rho 1 square by rho 1, that is rho 1. So, we can write straightaway 2 k by k minus 1, then rho 1 is going inside rho 1 square, and that rho 1 square by rho 1, that is rho 1, right. So, we will be getting P 1 into rho 1, and this P 2 by P 1 power 1 upon k, that will go inside as P 2 by P 1 power 2 by k, and then if we take inside, then we will be getting P 2 by P 1 power 2 upon k minus 2 upon k plus k minus 1 upon k. So, it should be k plus 1. So, that is P 2 by P 1 to the power k plus 1 upon k. So, that is the expression of mass flow rate upstream at the exit of the nozzle. Again we can see for the constant value of P 1, rho 1 and k, mass flow rate upstream is also dependent on the pressure ratio P 2 by P 1. And now we should try to find out what is the critical value of P 2 by P 1 for which the velocity would be maximum, which in turn will give the maximum mass flow rate upstream at the exit of the nozzle. So, if we now try to write mass flow rate per mass flow rate upstream per unit area. So, mass flow rate upstream per unit area, that is m dot 2 by A 2. So, that is nothing but under root 2 k by k minus 1 P 1 into rho 1, and that is P 2 by P 1 power 2 upon k minus P 2 by P 1 to the power k plus 1 upon k. So, this is the expression of mass flow rate per unit area, and as I said that say P 2 by P 1 equal to R. So, we can try to find out what is the critical value of R for which this mass flow rate per unit area should be maximum, because area is constant. So, if this particular quantity becomes maximum, then mass flow rate also will be maximum for a constant exit area. So, if we try to find out the maximum quantity of this, maximum value of m dot 2 by A 2, which in turn allow us to find out the maximum value of this quantity. In a way, let me tell you. So, the pressure ratio for which the mass flow rate per unit area should be maximum, as I told you, if mass flow rate per unit area is maximum, mass flow rate will be maximum because area is remaining constant. To get this particular value maximum, to get the maximum value of this quantity for a particular value of P 2 by P 1, which is nothing but to find out the maximum value of the quantity which is there in the bracket under root. So, that means our objective should be to find out m dot 2 by A 2 will be maximum when r power 2 upon k minus r power k plus 1 upon k is maximum. Try to understand. So, basically if P2 by P1 equal to r, then this quantity will be maximum when this will be maximum. So, to find out the maximum value, that means when dr of r power 2 by k minus r power k plus 1 upon k will be equal to 0, right. So, again this is very trivial. If we do this, then we can try to find out 2 upon k r power 2 upon k minus 1 minus k plus 1 upon k into r power 1 upon k. So, basically you know that from this equal to 0. So, if we go one step further, then we can find out 2 upon k by k plus 1 upon k, that is nothing but r power 1 minus 1 upon k, r power 1 minus 1 upon k, that is nothing but r power k minus 1 upon k. So, just algebraic manipulation you can do and you will find. So, this is the value of r, that means it will give the value of r equal to P2 by P1 equal to 2 upon k plus 1 to the power k by k minus 1. So, this is the basically very important aspect, that we have the value of r. So, this is the critical value of r, which is nothing but the pressure ratio, that is the ratio of exit pressure of steam to the inlet pressure of steam, for which the mass flow rate per unit area, which is again the mass flow rate of steam because area is constant, is maximum. So, our objective, whenever someone is designing the steam nozzle, designer must be careful to find out the critical pressure ratio, that is nothing but the ratio of exit pressure to the inlet pressure of steam when it is flowing through the nozzle, for which the mass flow rate of steam will be maximum. We shall discuss about the critical significance of the critical pressure ratio in the context of the nozzle operation, together with the design aspects someone should consider while designing the flow nozzle from this particular expression, and that part we shall discuss in the next class. With this I stop here today. Thank you.